This series we've been going through has really been looking at how to use basic tools like ImageJ or Fiji to do image segmentation and learning about how to use classical segmentation to solve image analysis problems. And that's sort of been leading up to today, where we can actually start to think about using more advanced tools, which are better at a lot of these difficult challenges, but also have to be used with a little bit of caution. And so the idea today is just to introduce you to some of these machine learning tools, and then give you like a crash course in practically using them for biomedical image analysis. And so if we think back to the previous week where we were using classical methods to perform image segmentation, we could have a simple image, like in this case, DAPI labeled inside some cells. And we could use thresholding to get a easy segmentation of those nuclei, then to make measurements on size or intensity and things like that. But of course, in biology, things are rarely this simple. And a good example in neuroscience is when we're looking at neurons in brain tissue, where they're can be very densely packed and they're surrounded by their axons and dendrites. And this becomes a much more challenging image segmentation problem. And if we just use a threshold, this will be pretty unsatisfactory. Of course, we could do background subtraction, and we could combine a number of filters and get a much better result at detecting those cells. But that would normally require a lot of work. We have to think about what filters to use, exactly what process to follow to get a decent result. And often what happens is you'll do that and then go to another brain or another section and find that combination of filters isn't giving you the results that you really need, and there's over or under segmentation. And a really good way to deal with this is to use machine learning segmentation. And this is an example of how we use Ilastik to detect both cell bodies as well as axons and dendrites. And just to give you an example, Ilastik is actually a really well-documented tool. We're going to go through using it today and some of the sort of finer features to understand to get a good result with it. But they've done an amazing job of sharing how to use it and to make it accessible for almost anyone. Just so you can see in the image there, you can paint background, foreground, and then train it to detect, or basically assign pixels with the probability of being one of these sort of classes, like foreground or background or cells and dendrites, things like this. And this is not just used in fluorescence microscopy, it's also used in electron microscopy to help segment cells and other organelles that have different contrast or texture that traditional or classical methods will be very poor at distinguishing between. And in addition to this, using deep learning for restoration and image segmentation is something that's really exploding, and there's been a lot of really exciting papers come out for this. And probably more recently, what's really quite helpful is that there's been a lot of effort in making these accessible to biologists. So you don't necessarily have to understand what's going on, you just need to understand how to implement and also the sort of caveats to doing so. And that barrier of using these tools has sort of been, it's getting removed, and hopefully by the end of today, you'll really feel that you can start to access some of these tools. And so why you might want to use deep learning over machine learning like Ilastik is, one, to deal with this noise problem. If you're at a microscope, maybe you want to spend less time at that microscope just to get through your project faster, or you might be working on something in live cells where phototoxicity and imaging speed become really important if you're trying to follow something that's very dynamic, that's not so fluorescent, and also it could be perturbed if you start to damage the cell. Then you need to start thinking about imaging with very noisy data, and then using something like a deep learning restoration tool to restore that signal, so that then you can go and segment the organelle or the cells or whatever you're imaging. And the other advantage is they're a lot faster to implement. So there's sort of this overhead at the beginning where you have to train the network, and they can be quite specific to a task. We'll talk about this later, but you don't want to fall into the trap of using a network that's been trained for one task on another task, because the results you'll get will be very unreliable. But once you've trained a network for the task that you're trying to perform, then creating the prediction, like in this case, the denoise data, is very fast, just a few seconds rather than tens of seconds in something like Ilastik. So a little bit of work at the beginning, but then much faster for the rest of your analysis pipeline. And sort of to try and get you excited about these tools, I just wanted to share some really good examples of these. Some of these have been around for a few years, and some of them are quite recent. There was a package and a paper that came out called CARE, which is using this sort of content-aware image restoration. And this is really where you train a network with a low SNR image or a very noisy image, and you have an image of the same fluorescence, but much higher, SNR. So, imaging with terrible settings, imaging with really, really good settings that you would never really dream of doing in a normal experiment because it would just take way too long. And you can train the network to sort of see, okay, when I have this noisy data, this is what it really should look like. And you can see in the image here, just how noisy the image can be and still get a result that's very high SNR. And so you can think about why this might be good, like we talked about, live imaging, but also solving segmentation problems. If you have really good SNR, like what you can get from these trained networks, then solving like where the cells are or where the boundaries are becomes much, much easier. And the other thing that's being used for is increasing resolution. So this is a really good example where they've imaged with larger step size or having lower resolution in the axial dimension, which is very common for confocal microscopy, but training it with data that's isotropic, and then the model becomes quite good at predicting what those sort of interpolating what those slices should be, and so this can sort of be a shortcut to getting you nice isotropic data for segmentation and measurement. Sort of building on this was some really great work that came out of Harry Schroff's lab. And this is a different type of network that's very good at restoring signal to noise. And they use it in combination with their ISIM instrument, which is very similar to the SORA system that we have at the Institute. And so they want to image very dynamic processes in cells. And these are very sensitive processes. If they image with enough laser to see it clearly, then the process is perturbed. So they need to find a way to image quickly without damaging these processes. And so they've trained this RCAN network to restore very noisy, just in the same way as we just talked about, raw data that's very noisy, raw data that has very good signal to noise. And then they can just image very quickly from then on and restore that data to something that they can get useful measurements from. And they sort of extended on this and did something which is just fantastic. They took cells and used expansion microscopy, took the expanded cells, imaged them using ISIM, and then they sort of downsampled them and put a sort of a blurring on those images so that they would look very similar to what you would get if you were imaging just using normal ISIM or SORA imaging. So then they have a ground truth of what this high resolution data should look like. They have what you would normally get imaging on the microscope, and train this network to both do denoising and then the sort of image sort of increased resolution. And the results they can get doing this, it's noted there, like almost 2 times improvement laterally and 3.6 times axially. And you can sort of see, just looking at the orthogonal view in the bottom image, just how how much which image would you like to be working with if you had to make those measurements and do that analysis. And importantly, in this paper, they also talked about the linearity being preserved. So you could make measurements of the intensity, and those would actually be useful measurements in terms of how much protein was there in the data. Some other things that are quite useful. This is a very recent paper using neural networks to do interpolation for live imaging. So if you're doing imaging, you know how difficult it is to get good data at the frame rate that you might want. And if you're trying to track things like mitochondria or other organelles, being able to image with better resolution and sacrificing a little bit of time, but then being able to sort of restore those frames that you're missing is something that's very powerful. And this approach is much better than sort of typical approaches people use to sort of estimate where those objects are between frames. And so this is something that they've recently released and is available to sort of start to improve sampling. Use like 2-fold, but also 4-fold examples are still quite reasonable. Okay, so there are all examples where we're trying to improve the data for segmentation. And of course, there's other examples where we're actually segmenting. And we'll actually use StarDist today as a quick example of how you can segment nuclei and cells. This is a really easy tool to use and is much more easy to use in terms of trying to get a good result than sort of fiddling around with different classical filters and segmentation tools. And then importantly, this is what we're sort of focusing on today for this practical, is how to access these tools. I mean, for a while, there's many of these papers coming out, but if you're a biologist, you can read the paper and you might be excited about using it, but then there's this big barrier of, okay, well, how do I implement this on my data? How am I going to train this network? And you'd have to invest a bit of time in learning Python and getting comfortable with implementing these models. But that's not the case anymore. And there's been a lot of work in making these tools available to everyone. And one good example is DeepImageJ. This paper came out quite recently, but a lot of tools are already available from within DeepImageJ. And we'll actually dive into this during the practical today. And just to give you an example, these are some of the, this website BioImage.io is where people can train models and then share them, so with a publication or just to share with the community in general. This sort of say, if it's a very similar problem to yours, then you can just find these models and see if they work for your data. Otherwise, you can train your own model, which we'll look at today, and share that with other people. And so this is something that's really starting to take off. And I think for many people, this is something that can really be a game changer for the work that you're doing. There's also been work in making a lot of the denoising tools available. So this is some examples of some of the recent, Aiden is a very recent tool that was made available for sharing denoising algorithms. So this can be algorithms that are like neural network. They can just be, standard machine learning as well as classical denoising tools, but they've gone to a lot of effort to make these accessible to anyone and combine them with a lot of tools for things like motion correction and regular noise and other things that we're often facing when we're trying to do advanced microscopy. So I'm hoping these slides just really stimulate you to think about, okay, these are things that are available and things that I can start using for my research. And then I don't want to forget to mention this zero cost DL for microscopy. This is an effort from Enrique's lab that's really gone a long way to making these tools available to everyone. This is not something we'll talk about today. This is using Google Colab. But the great thing about this is, a paper can come out and very quickly there'll be some tools available on Google Colab using this zero cost DL to allow you to start using it. And essentially you can have data locally, upload them through Google Drive, use these Colab documents to sort of train the network and get results. And so this is a really fantastic resource and something you should look into. And then, in terms of what we'll also be looking at today is using a tool called CSBDeep, which does a lot of this denoising as well as segmentation. And there's a nice pipeline, denoiseg, which combines denoising and segmentation to give you really nice results for segmenting cells. And so we'll be looking at this specifically. But before we get started, I really just wanted to point out these things need to be used with care. So these are very powerful. There can be some hesitancy, I think, with people who are really not sure how these things work and whether they should be applied to biomedical imaging. But there's a really clear case now that these are tools that are appropriate when there's very challenging experiments. And in some cases, especially for live imaging, it's just not possible to get data that's easy to segment without using these tools. But you have to use them with care. And I think the biggest example is, making sure that you're using a network that's trained for that task, like we were talking about. So if you've trained something to denoise, in this case, actin fibers, don't try and use that for mitochondria or something that's quite different, because you'll start to get artifacts. And an example here is this, a network that was trained on doing something else, trying to restore these filaments and getting something that's really not reliable. And so that's the one thing that you need to have in mind, is taking the effort to annotate data, train a network for exactly what you want. And if you do that and use it in that context, then you'll get very good results and it should be very reliable. And we'll look about how to do that today. And then just finally, if you really want to learn more about this, we sort of touched on some of these papers today, but there's some really good, all these papers in Nature Methods are really good at going through like the applications, the limitations and how to avoid problems when you use this in your research, as well as some of the really good examples where they've been directly applied to biomedical imaging. Okay, so with that, what I'll do is I'm going to log into the workstation at the Zuckerman Institute. Okay, hopefully you guys can see that all clearly. So the first thing that I wanted to go through today was to show you how to use Ilastik. And the main reason for that, maybe you're thinking why after seeing all these great examples with deep learning, but Ilastik is something that's very accessible and it's easier to understand, and you can see how it's working and also apply it in an automated way. And so hopefully if you're trying to follow along, you'll have Ilastik installed. I'm just going to run it here. And just as the first example, we'll actually use those data sets that were captured in brain tissue, because I think for neuroscientists, this is a really common problem in terms of segmenting cells as well as axons and dendrites. And hopefully you also have, in that example data that I've shared, you'll have these three sections. These data sets, maybe just look like cell bodies if you open them up, but they're 16-bit data sets and they've got quite a range of intensity. So if you actually adjust the way that you're looking at them, you'll see that there's actually a lot of projections in these data sets as well. So it becomes quite challenging if you're trying to approach this problem using classical methods. You'd have a really hard time of it. So when you start Ilastik, you have a lot of options here. What we want to really focus on today is pixel classification, and then I'll show you how to also use object classification. And this is actually where you can, detect objects like cells and then use features of those objects to start to classify them as different cell types or in different cell states, which is really powerful. So if we run this pixel classification, we'll need to create a new project. I'm just going to put this on the desktop. Okay, so the very first step here, it's asking for some data. And you can really just drag and drop data at this point. So I'm going to select our three data sets here and drag them into the main area here. And the first thing actually that I'd recommend doing, if you're going to train a project for Ilastik, make sure that you copy these directly into the project file, because right now they're just relative links. So if those files get moved or deleted and you want to try and make some changes to this project, you'll find you won't be able to. As soon as you open it up, it'll note that the links are missing. You can still use it for batch processing, but you won't be able to make any changes or audit how it was trained. So if you select these and right click, you can edit their shared properties and change the storage to copy into project file. And that way these become part of the project file. The file's a little bit bigger, but you can just take this anywhere and modify it, and you don't have to worry about there being any problems down the track. Okay, so we've put these files in. The next step is selecting features. So the way that Ilastik works is, in our normal case with classical filtering, we'd do some filtering, we'd try some different segmentation, and then that would be, whatever was out of that would be our final result. The sort of power of Ilastik is that we're using many filters. So when we select features here, this is sort of like the kernel size of the filters we're using. So if it's just very fine features that were important for determining the things we're looking at, we could just use some very small filtering. If there's, information that could be like a lower frequency information that's useful, then we could use larger filters. For this type of data sets, I find that using up to about 3.5 gives quite good data. If you go too high here, you'll often find you'll get halos and things like that when you're trying to segment. So if you're seeing things like that, it might be a good idea to tone this back a little bit. And so what these are is, these are going to be the filters that are generated at each of these scales. So there's going to be some smoothing, some other filters which are quite useful for finding edges or features, and these texture type features which are quite useful in, if there's sort of different labeling, if it's homogeneous or has some kind of texture to it, then these filters will help, pull those features out. And so when we select these features, Ilastik is quite good, and it actually will show you what all those features look like. So, if you're trying to use Ilastik and you're trying to save time, you might find which filters are most useful in informing Ilastik of, things being a cell or a background, and leave those in and take the other filters out. And that way Ilastik will become faster. But you can click on any of these and you'll start to see, okay, for this filter, this is what's being generated. And, some of these other ones are a little bit longer to generate, but you can see there's other different information from these filters. And so when we're training Ilastik, it's using a random forest decision tree to figure out what the probability is that each pixel belongs to the cell or the background using information from all of these filters. So after we've selected these features, we can go to training. And the first thing that you might have trouble with is being able to train it properly. So, so just to give you an example, I'm just going to call these cells. And we use this a lot, for doing axons and dendrites as well. So I'm just going to call this one projections, and this will be background. So we've got 3 colors here, and we want to start training. But before we start training, it's a good idea to see what the data really looks like. And so I don't want to accidentally train background if it's a projection. And so if you come down to raw input, you can right click and say adjust thresholds. And this is where it's automatically scaling the image. So it thinks it's helping you, but in our case, because there's so much information in the intensity sort of scale here, we need to turn this off and bring the maximum value down. And that will give us a better chance of seeing like where our cells are, as well as where the true background is. Okay, so let's start training. And when it comes to training, less is more. So we don't really want to train too much at this stage. I'm just going to zoom in. So to zoom in, you can hold down Control and mouse wheel. And we can start by training some cells first. So I'd find like a few different cells, and I would just paint a little bit in each of the cells. Maybe this is an example of a fainter cell. And then for the projections, and you should be really careful with this, like, if you notice that you've painted a couple of pixels that really aren't projection pixels, then you want to delete those, because that's really going to affect the final result. So in this case, I'll just do a few clicks in here. We don't have to get it perfect at the beginning. What we can do is start to get a preview after we've done a few clicks, and then refine it very quickly from there. And then for the background, I could say somewhere in here is probably background. Maybe out here as well. And if I start a live update now, it'll start to color in, okay, what it thinks are cells and projections. And it's running a little bit slow because we're on Zoom and we're also using a remote desktop. But what we can do now that we're seeing how it's looking, I can see areas where this should really be projection, even though it's got a little bit of yellow. Hopefully that's coming through clear enough for you guys. I want to make sure that the cells are all pretty good. So again, you can hold down, so Control and mouse wheel zooms in and out. Shift and left clicking will pan around. Maybe I want to get a little bit more. I mean, projections are looking pretty good. I mean, it's already looking pretty good compared to what we'd be able to do with, any other kind of segmentation. So we can refine this a little bit more, but you can sort of get the idea now. What I find really helpful to sort of start to speed this up is I turn on the segmentation for cells. And that really gives me a good idea of where I should target to improve this. So I can see, okay, this is saying it's cells, but it's probably projections or background. So I can click in here with projections and start to fix that up. I can see like this should really be background probably, so I can put that in here. And we can start to see that it's looking better. We're not going to actually get this to be perfect, because what we really want to do is some background subtraction beforehand. But I wanted to show you like at least what this would look like. And we can also check what our projection segmentation would look like. It's not too bad actually. It's still missing a cell here or two, but this is already quite good. And I'll show you how to get it a little bit better in a minute. So if we wanted to export this and use it somewhere else, then we can come into prediction export. This is, we want to export the probability. So in this case, every single pixel will be assigned a probability of being, how much it's a cell, how much it's likely to be an axon and background. And we want to export those in a way that's easy to interpret. The default is to use HDF5, which is a fine format. This is really good, especially for large data sets and things like that. But it's a little bit more tricky to use straight away in Fiji. And so if you're just doing simple analysis, it can be quicker just to turn this into a TIFF file. And what we want to do is convert this, because they're probabilities, we don't need much information, just 8-bit is fine. And we can renormalize the data so that it's 0 to 255. So basically an intensity of 255 would be 100%, and 125 would be a half or 50%. So, and the other, if you only care about the cells and the projections and you don't need the background, or maybe you only care about the cells, you can tell it here, you don't want every channel. We just want channels 1 and 2. That's the cells and the projections, or 1 would just be the cells. Okay. So that's it. We've trained this project. We could save it. And if you wanted to process several images from within Ilastik, we can just go to batch processing here and select some data. And then just batch run that, and it'll give us a result, which we could look at in Fiji. And you can see we've got our cells and projections here. Okay, so Ilastik's great, but sometimes you need to give it a little bit of a help if you want to get a good result. And so I know from experience, I can get a much better result if I do some background subtraction for these kind of data sets first. And so what I'll just quickly do is and we talked about this in a previous session, how background subtraction works and why it's useful for data like this. And for these kind of data sets, we can use something like 14. I'm just going to do 2 here. And of course, if we were doing lots of images like this, we wouldn't be doing it this way. We'd make a small script and just run it through the data set. Okay, so I'm going to leave this one open, but I want to run a second Ilastik to show you, hopefully this won't be too slow for us, but okay, good. So I'm just going to leave this open, just to give you an example of how the background subtraction is better, and then also to show you how object classification works. We'll run this pixel plus object classification, and we'll use our background subtracted data. Okay, so we're just copying them in. I'm not going to worry about saving in the project, but I would if I was going to use this for something later on. I'm going to select the same features. We're going to do our training. And you can see already we have much better contrast now. So it's going to be a little bit easier for Ilastik to give us a better result. Okay, so I'm going to zoom in again. I'm going to do some cells here, start the live update. You can see areas where the projections are kind of ballooning out a little bit, like they're sort of looking too large. If that was a problem, then you could come in with a background and just try and find a pixel that's nearby, and that will shrink them in a little bit. So you have something that's a little bit more closely matching the data. Areas where there can be a lot of problems for this type of data is where the projections are very dense. They can start to look like they're cells. And so this is somewhere where you want to focus a little bit more attention. And there'll be some parts in the brain where you probably find you'll have false positives. And this is where, I'll just turn this down a little bit, but this is where you would probably start to use a deep learning tool to get a better result, because there's some areas where, Ilastik still can't quite get there. But hopefully it's sort of already apparent that this is a better result than what we were getting before. And I could turn my cell segmentation on to see how it's looking. Yeah, so hopefully this is giving you a good idea of how to tackle this. And you should find that, within a few minutes, you'll have something that's very good. And of course, if you're planning to use this for, a project, what you would want to do is include multiple images from multiple animals and have something that's quite robust and reliable across the whole data set, because you don't really want to be changing this project, changing the Ilastik project in the experimental project, because that'll start to give you different results. So you should find if you spend some time here refining it, you'll get a result that's actually quite good. Because we added multiple data sets, you can actually view them here. So right now I've been training on this image, but how does it look on an image that I haven't trained on at all? And so it's really useful to have multiple data sets to check. You can see, even though it hasn't seen this image before, based on the training I've done, it's actually already pretty good. And so you'd want these to be kind of diverse images, so images where there's very dense projections, images where there's cells. So you have a very good idea of how this project's going to work for your analysis. So if I was going to spend more time on this, then I would focus in on these projections and I would get this a little bit more accurate. But I'm just going to move on now and go on to the next step, which is where we can start to look at thresholding these probability images. So in this case, I want to focus on the cell channel. So we're selecting it here. 0 is our cell channel. And we're using a threshold here. So anything above 0.5, so anything above 50%, that's going to be what we consider to be a cell. And then we've got a size filter here as well in case we've got some debris or things, that a few pixels that aren't really cells. We can apply this and start to get a result. You can see like, some of these ones here, they're quite small and they're not really cells. I would probably go back and improve how it's actually trained. But if this was as good as you could get it, you could start to actually use a size filter to get rid of some of these. There are some cases where you might have cells that are very close together, where we don't really have a good example of them here, but if you have a lot of cells that are very dense and they're starting to fuse together, you can use a different technique. So this is just a simple threshold. So we basically have a cutoff above 50% probability, that pixel is definitely a cell. And we could obviously play around with that to be higher or lower. This hysteresis threshold lets you have like a higher threshold for maybe the center of the cell, and then a lower threshold for where that cell boundary cuts off. And this can be quite a useful way of being able to separate cells a little bit easier in the data set. So in this case, like the threshold here is too high. Maybe I need to have this at 0.5, but maybe I would be able to adjust this a little bit to get a result that was maybe nicer than what I was getting using a simple threshold. So you should be aware of this and find a setting that's giving you a good result in terms of segmenting the cells, even if they're close together. Okay, so say we're happy with how we're going with these cell detection. What we can do on top of this is start to classify the cells. And so this could be a good example is if you had cells that were undergoing division, or maybe there was some different about them in terms of their intensity or shape. Maybe, if you had really high resolution data, maybe you could actually tell what cell type they were based on the morphology of the cell body. There's a whole lot of things you can think about for this. And this feature selection here lets you do just that. So we can tell it what features we care about. That we'd have to look in here and say, okay, I know that the circularity is different for these cells. Like some are very straight and some are very round, and so I could use those sort of features to sort of filter the different types. I'm just going to choose standard features here, and we don't, in this case, we don't really have different cell types. So I'm just going to select in the next step. I'm just going to select one cell, and so that will just become all the cells. Because all I really care about in this case is just exporting these cell detections. So I've got a number of how many cells, or I could do some measurements in ImageJ or something like that. And so here is where I can export these. Yeah, what I wanted to show you in here is like if we just do the predictions, we're just going to get an image that's just the cells. But what can be more important is maybe having object identities. This way, this is kind of what we did in the previous workshop in ImageJ. Every single cell will have a different intensity, and that can be useful in terms of just differentiating the cells rather than having just a mask where every cell has the same intensity. And again, we might want to choose some settings that are useful for us. If we're working in ImageJ, then I find it's a little bit easier to have them as TIFFs. If we've got a lot of objects in the images, I wouldn't choose 8-bit, because then if there's more than 255 objects, it's going to max out. So something like 16-bit or maybe 32-bit if there was many cells. And then we can normalize here and then change this to TIFF. And then we'll have a working project for this. Okay, so what I showed you before is we just run this using batch processing. So we copy the files in and run it from Ilastik. But you might want to end up doing something a little bit more sophisticated. Maybe you have some raw data from a microscope. You need to do some processing like filtering, or like I did the background subtraction. Maybe you need to enhance it with another filter first. And then maybe you want to do some analysis afterwards. So you might want to make some measurements on the intensity of another channel, or do anything that's more complicated than what we can do in Ilastik. And so to help you along with this, I've shared in the folder a macro. So we can open that up and have a look together. This is a macro, and if you joined the workshop last week, you would see like how we can create these macros. But in case you missed that, then we can just go through it together now. This initial steps here are just to initialize and make sure that we have some settings for doing the segmentation consistently. So having the foreground is white, the background is black. These are things that can sometimes be an issue with Fiji if you're trying to do these things repeatedly. And then we have some parameters that will load in the data we want to process through Ilastik. And in this case, we're also doing some processing beforehand. So just like I manually did that background subtraction at the beginning, we can just do it automatically here. So we can do some background subtraction, and this, I've left these in from a previous project. In case you need to do unsharp mask or some other kind of pre-processing, you can do that too. This is where our project is located, so we need to point it to the project, and we also need to tell it where our Ilastik is. And then, just so you understand what's happening here, this first step is to really make sure that the folder that was selected is a folder and not a file, to detect all the images that are inside that folder. So we don't want to process text files or other subfolders. We just want to get all the images, and that's what we're going to process. That's what this step is. And then we're making some folders. So I find like it's important, especially if you're trying to validate how something's working, or if you need to audit what's happening. We want to look at the intermediate data. Maybe later on we can turn that off, but right now we want to check that. And then we also want to see what the Ilastik outputs look like. So this is just creating folders for the enhanced or the sort of intermediate data, and then Ilastik outputs. And then for every file in the folder, we want to open it up. We want to know which channel we're going to process through Ilastik, and then we're going to do any pre-processing. And so that's where we can do the background subtraction. So here we're just saying, if the background subtraction set is above 0, we want to do background subtraction, and then what background subtraction will we use? And this BG sub is the variable that we're setting in the parameters. So just to show you, right now it's set to 5. I actually want that to be 14. So if I ran it with 14, that's what's going to be inserted here. And then I've just commented this out, but this is if you were going to do unsharp masking or something as well. And then we're saving that. So this is going to be the enhanced file. So I'm just calling it, this is the directory where the enhanced file goes, and this is the name. So the name is the raw file name plus this background subtraction. We can actually just put this in here as well. Then we're running the Ilastik processing. This is actually a function that I've written in at the bottom, but all you need to do is tell it the directory Ilastik's installed, the project that you're using, the enhanced, like the output name, and the folder where it's going. I've also left this in here, but it's commented out, and this is just in case you want to do something where you overlay the Ilastik output with the raw data. So, a good example would be, okay, we've processed this through Ilastik, but we want to use those masks now to make some measurements. So maybe we want to measure the intensity of a couple of different channels using those masks. Or maybe we just want to take those masks and just put them on top of the raw data and use that to validate how well Ilastik is working. And all of that can happen in here. So this is a very basic one. I'm just copying the Ilastik results into the series of channels and then saving that as a new file. But you can do any one of the things that I mentioned before, or something entirely different. And that would all happen here. And then at the very end, we just close all the data and move on to the next file. So this is a nice way of processing serially all the files in the folder. And we won't really spend too much time here, but this is just a function that I found works well enough on PC to run Ilastik. And then this is the function for creating the file list. And we talked about this actually in the preview. So if you're having trouble following this, or you want to learn more, then I would look at the previous week's workshop, and that goes into this in quite a good amount of detail. Okay, so how does this work? We can try it out. So this is our raw data folder. So I'm going to choose our mouse brain sections data set. The channel to be enhanced, well, there's only one channel in this case, so we'll just leave that as 1. And I found that 14 is good for this data set in terms of removing background, but leaving the axons and dendrites and cell bodies. We want to tell it the project to use, so that could be the one we just made together. And the Ilastik location, this is where it's installed on the computer. So just make sure that you've got it installed and point it to that correct directory. And we're using post 3, which is the stable release of Ilastik. Okay, so let's just run this and see. So we're going to have a little log file here that's telling us what it's up to. There are ways to run it like in batch over several folders using scripting, but if you have a lot of files, it doesn't work. And so just to get around that problem, especially if you're processing tens or hundreds of images like we sometimes do, this macro will just process one image at a time. It's a little bit slower, but I think it works out to be maybe 10 to 20 seconds per image. So it's not really that bad. give you an update here telling you, okay, that it's processed the first image. Now it's working on the second image. And if we go and look in that folder, we have our enhanced folder. So this is where the images have been enhanced. So with the background subtraction in our case, and this is our Ilastik output file. And if I open up these, then hopefully what you'll see, so it's finished. So if I can open up one of these. And in this case, we're just saving the, these are just masks. So what we want to do is go in and make it so that, I mean, this is fine, but if we wanted to have the ID number, then we want to change our project so that it's actually saving the ID as an intensity. So this would be like an intensity 1, intensity 2. And that way we could actually differentiate these different cells with an identity number. Okay, so that's how to use Ilastik in a Fiji macro. Yeah, so what I also wanted to spend time on during this workshop was to show you how to use these deep learning tools, because they're incredibly powerful. And I think for many people, there's kind of like this barrier of getting started using them. So I'm hoping that, just in a short time we have today to really just remove some of those barriers so that you feel comfortable in using deep learning in something as comfortable as Fiji. And so to start with, we can use an easy example, which is the StarDist cell detection tool. Let me just clean this up here. So there's another folder that I shared with you guys, which is just some, nuclear labeled cells. So like a very simple data set. And, we could play around with like adjusting threshold. It's not a particularly challenging data set, but, if you just wanted something that would work quite reliably and there was, quite a lot of variability in the images that you were working with, then we could use StarDist. And, if you want to have more information on StarDist, here's the website for it here. So you can just search for StarDist and, microscopy. This will come up. It's very easy to use, and it's very easy to install. I can show you now how we would install it. So you should know that with Fiji, we can add multiple plugins on top of the plugins that already come with it just by going to Help and Update. And this will update all the currently installed plugins, but what it can also do is let us add in plugins that other people have developed. And so in a second here, what we can do is just go and look for the plugins that we need. So we need two things. We need CSBDeep, which gives us a lot of the tools for doing, the TensorFlow and running these networks on a computer. And you don't have to have a GPU to use this. So you need a GPU. We'll go through this in a minute, but you need a GPU for doing the training and to run these things quickly. But even if you're just on a laptop without a good GPU or an NVIDIA GPU that can do this type of work, you can still run these tools on your CPU. If we go to manage update sites, we can find the CSBDeep. So I already have it installed, but this is where you would check on. And StarDist is just here. So if you update those two, close this, and then it'll have an option here to update Fiji and then restart Fiji. It'll all be over within just a few seconds. It's not a lot of data to download. And then what you'll find after you restart Fiji is you'll have StarDist available just here. There's also a 3D implementation. I'm not sure if it's available in Fiji yet, but it is available. This is a 2-channel image, so I just need to split this into 2 colors. And then I can go to StarDist. They have like some advice on their website about parameters here, but especially for data like this, it's pretty much ready to go. We can just run this. And here's our result. So these will be, it automatically puts them out with an ID. So if we hover the cursor here, you'll see that these have different ID numbers. There's some small ones here that could be errors. So, what we could do is straight away, we could just, if we were trying to like get some more information on these, like maybe we want to make some measurements or measure some intensity, we can use our standard particle analysis now that we have these masks. So I can like create a new threshold just with Control-Shift-T. I can make a threshold that just selects all of these cells and then start to make measurements. So if I apply this, then I could start to measure like, a different channel, how intense it is and things like that. And I did share, this is something that should definitely be in there, is a macro for you to use this. I mean, it's very, especially if you've been to the last workshop and you saw how to create these macros, it's very easy to put in that one line for StarDist. So just to very quickly walk you through this, we have some settings here just to make sure that the segmentation always works the same. So these are settings to make sure that the background is black, the foreground is white. These are things that can sometimes create issues if you're doing scripting in Fiji. And we have some parameters here, which if I run, this is just the directory where the raw data is and the channel that we want to do the segmentation on with StarDist. And then below here, we're just checking to make sure it's a folder. And then if it's a folder, we're looking at all the image files that are in that folder. So we're just getting a list and making sure that they're only images. And then for every file, we can open it up. If it's multiple channels, we can split it into channels and select the channel that we care about. And then this is the StarDist line here. I mean, it's a little bit of a long line, but this is all the parameters that we need to get a good result for our cells. And then we can save that as an output. I mean, this is just very straightforward. In here, you could actually, do some thresholding like I described, have the rest of the images open so that you could do some processing on them and then save the results or save the measurements, and then maybe even save an overlap image so that you have, the raw data plus the mask so that you can later on validate, okay, how well did StarDist work, which is something that I would definitely recommend. And so we can run this. Hopefully you've got StarDist working on your computer and you can just run this macro. I can tell it that it's channel 1 that I care about. Also, in this one, I think we haven't got, so these images popping up, this is something you really wouldn't want to have happening. It's nice to see what's going on right now, but if you want this to be working much faster, then of course we would use a batch mode. So we would just say here, like set batch mode, and we would say it true. And that way this whole thing will run a lot faster and won't pop up any windows. And if we go in that folder now, we should have our output. And this is just a simple case of showing those masks, but of course we could do something a little bit more complicated. Okay, so that's a very easy introduction to using a already trained neural network. The one that I think is really powerful in terms of getting a hold of existing trained networks for your data is DeepImageJ. And this again is just a very simple update. So if we go in here and have a look, you'll find the update site for it. It should be listed in Fiji. In here, DeepImageJ. And once you've got that installed, you'll need to restart Fiji. So this is important if you do have a good computer with an NVIDIA GPU card, when you install these deep learning based tools, they're not going to be using the GPU. So if you do have that hardware, it's really important that you make a few changes to the Fiji installation. Actually, I'll show you that now just so that you know how to do that. So I'm just going to close these. So once you install these tools, the very first thing, so if you go into options, the very first thing you want to do is just see how TensorFlow is sort of being used on the system. So under options, there'll be a TensorFlow option. And because this is one of the workstations at Zuckerman, I've already set this up to be working on the GPU, but what you'll probably find is that you'll have it using a CPU. So if you have a GPU that can use CUDA and the neural network tools, then the first thing you want to do is select one of these GPU-enabled TensorFlows. So I've got that already selected here. And the other thing you'll need to do is make sure that you have the right software installed so that you can use this properly. So this will install the TensorFlow version, and it's telling you here what you need to also be installed. So these are the tools to use the NVIDIA card, and this is specifically so that you can do these neural network training and predictions. And it's telling you exactly what versions. So I think one of the main barriers for people is they know they need these things, but they just go and download and install them, and invariably you'll end up with versions that are mixed matched, and it just won't be using the GPU properly. So just pay attention here and make sure that you are installing the correct versions for what you're trying to do. And it's very easy to get access to this stuff. The CUDA toolkits, you can just Google search. You'll find an archive if it's an older version that you need to use. Like in this case, this is a little bit older now, but this is the one we need for this. And The neural network tools, they're not immediately available for download, but all you have to do is create a login account with NVIDIA, and there's no real barrier to doing that. So once you've created an account, you'll be able to download the DNN tools. And there's an archive list there for all the different versions that you need. So once you've done that and enabled the TensorFlow and you have a GPU, then it should be using the GPU, and you'll get some feedback if it's not doing that. And then, if it doesn't do that, it'll just use the CPU, which will be very slow for training, but okay for doing some of the predictions. So once you've done this, we will have DeepImageJ here. And to run it, we really need to have some models installed. And it's actually very easy to do. So there's a website called BioImageIO. This is kind of an effort to make all these tools available to people, not just for DeepImageJ, but for other platforms as well. People are sharing pre-trained networks. So, if you're lucky, there's something in here that's very similar to what you're trying to do. And there'll be examples of, restoration, as well as, some great examples of sort of converting bright field or DIC images into images that you can get nice masks from. There's some really great things that's already available for this. And any of these, they'll have some example data sets, so you can see how the network's supposed to work, and then you can try it out on your own data. If we just download an example. So I'm just downloading it here. We're using DeepImageJ. So this sort of contains all the information that we'd need for this particular model. And you can just extract this. If we just make a folder for this, and UNet is a type of convolutional neural network that often gets used for these image segmentation pipelines. And with this, you just need to put it in the ImageJ folder. So if you don't know where that is, you can just look at the properties and find the location where Fiji is installed. And this is just like the same way that you would install a plugin for ImageJ. And there'll be a models folder here where you can put models that you've downloaded. So we'll need our example image. DeepImageJ. And then here's our, and in fact, I've got a couple in here. I've trained some in CSBDeep, but this is the one that we just downloaded. It's already sort of knows all the parameters it should use, because it's these sort of zip files that you download include everything so that it knows how to work straight away. And there it is. So we've used that model that someone shared on the BioImage website to do like what would be normally a challenging task of getting especially some of these boundaries that are very noisy and weak. To use a classical tool would be very hard to get a good result, but just within a few seconds you've got a great result using this network. I should just point out too that so these are already, they use the neural network that's been trained. And they also have some pre and post processing. So if you want to get in and start modifying what you do to the data before you run it through the network and what you do afterwards, you can just modify these. These are just the same sort of thing we've already been doing. These are macros. So you'll find in here a pre and post. Pre macro. If I look in here, this is all the things it's doing to the image before it goes into the neural network. So hopefully you're starting to get a bit more familiar with this process now of how to use macros, and then of course combine them with these neural networks. And I didn't have the recorder open then, but again, this is a macro recordable tool. So running this, keeping the recorder open, you'll get the information so that you can incorporate this into your existing pipeline. And yeah, that's basically it. So they're incredibly powerful, but you just have to be making sure that you're using them for the right job. So if I was doing something and there wasn't a model that was already available on this resource or other resources that are around, then you really need to train a network by yourself. And so this is something you would actually normally do through Python as well, but it's actually not too difficult to do through Fiji now as well. These things are improving very quickly, but the one that I wanted to show you today, just because it's an easy example to show you and also very powerful, is part of the CSBDeep toolkit. So we talked about this actually in the presentation at the beginning. So CARE is this image restoration. There's also noise to void, which is a really useful way of getting rid of noise in data. And denoiseg is combining this, denoising with image segmentation, which is a very common problem that people want to solve for a lot of their projects. And so if you look in here, they're really quite good in terms of giving you information of how to set it up. Of course, you can do these things in Python, but you can also use it in Fiji. And, actually, really all you need to do is what we sort of talked about. You'll need to, use the update site to add CSBDeep, which we've already done for StarDist. And importantly, if you're going to train a network, you really need to have a GPU, and you want to be, an NVIDIA GPU that has the CUDA capability. And we have that available here at the Zuckerman Institute. So this computer workstation 2 is ready to go for these type of things. And of course, you'd have to set it up under options to make sure you're using TensorFlow and things like that. And so once you've done that, underneath plugins, you'll find CSBDeep is actually all the way at the bottom here. Here's denoiseg, and what we want to do is we want to really, to start off, we want to train a network to do what we're wanting to do. So a good example for us is that example of segmenting the neurons, and maybe you want to know how can you actually go about doing this. So what I wanted to show you is just kind of the workflow for doing this. This is something that we can do on the microscopes using NIS elements, but maybe you want to use something that's completely open source and be able to share that easily with other people. And so doing it this way is kind of a little bit nicer for that reason. And so this is some example data. So when you're doing this type of work, you need to have a couple of data sets. You need to have your training data set that has the raw images and the masks. So, in our case, I can show you these are data sets actually very similar to what we worked on. So, we have our neurons and we've got a lot of projections. It's very difficult to get good results just using classical tools. And then we've got some masks. So for this data set, so I've got files from 1 to 12. And for exactly those data sets in this masks folder, I have annotated masks. So, you could get these masks. So you want to this is like where you have to spend a bit of time. You want to make sure that these masks are very accurate, because if there's any inaccuracies in them, that's going to flow through to how the network will interpret new data. So spending time here to really carefully annotate them will pay off. And the easiest way to do this, one way, if it's a relatively easy job, you could use Ilastik to start generating these masks. Because we have access to NIS elements, another really useful way, which I'll just quickly show you, is to use Elements, because it has a really nice tool for annotating data quickly. There's also some freely available tools in ImageJ for doing these quick annotations, but this method in Elements is very fast. So I just wanted to quickly show you this. But yeah, this is really the hard work in using these neural networks, is spending the time to create these training data sets. And denoiseg is quite good in the fact that it only requires a small amount of data. So you should be able to get good results even with just 10 to 12 images annotated, so that actually it's not as data heavy as some of these other networks. So if you want to annotate data and you have access to elements, and we have this on workstation 1 and 2, you can use their binary tools. I'm just going to open up that same image. So we should be able to, underneath analysis tools, there's a binary toolbar. Hopefully you guys can see that. So, a lot of annotation tools require you to go in and maybe draw. It can be very slow. So let's make this a little bit brighter. So, if you've got this open, then this tool here, it's like an auto select tool. You can just very quickly use this to, and I'll make this grayscale so you can see. Just left clicking, it'll quickly sort of, try and figure out how to connect all these things together. This is like too lower threshold. I'm just using the mouse wheel to scroll back. And so I can scroll down to like what I consider to be the cell, and then just right click. And then I can just go to the next one, right click. and so on. So this is a really fast way of annotating data that might take you a really long time elsewhere to just get a good result very quickly. Yeah, so hopefully that's very clear. So once you've done this, maybe I would do this a little bit better if I was going to use this for research, but just to give you a quick example, that's how you can mark the cells. And then you can convert these into a image. So if you save this image right now, it's just going to be looking like the raw data. You need to come in here underneath the binary tools here and convert binary to a color component. And what this will do is it'll make a new channel. So here's our raw data, and then this channel is our binary channel. So very quickly, you can have a bunch of cells. Maybe you do some automatic detection, fix it up with this very quick selection tool to get the rest of the cells. And then, also just while we're here, if you press tab, you have this sort of painting tool. So, if you find that some of these cells are not quite accurate, you can just use this these paint brushes to paint background. So you can very quickly fix up a few pixels that are inaccurate. And then you can just export these as TIFFs. So you could export the raw data as TIFFs and then export the masks as another series of TIFFs just by exporting one channel at a time. And that's within a few minutes, that's literally how I made the data sets that we're looking at here. I mean, there are ways in Fiji, but I find this is a really fast way. And so when we're training networks, we want to have some test data as well. So these train folders, these are the folders that we're showing to the network. Okay, here's the raw data. Here's the binary mask that we want on that raw data. And then we have some training, some test data, which is data the network hasn't seen. And we're seeing, okay, how well does this network perform on data that it hasn't seen before? And we can compare that to what the sort of ground truth or what the real masks are and get an idea of how well this network is performing. And so it's very easy once we've trained this to use it. So underneath plugins, we have CSBDeep, denoiseg. We can go to predict. I just need to select the data. So I think the one on this one here is the raw data. This is so when you train it, actually I can just very quickly show you what it looks like when it's training. They've made it very easy to use. So we can do the training here. And I've made these folders so that they're easy to interpret. These are our raw data images, the images for labeling. This could be the cell bodies or the axons, whatever binary image that you're trying to train it for. And then these are the validation or the test data sets. And these are the parameters that you'll need to use to train the network. You can play around with these to improve it, but these default settings actually work quite well. And then once you click OK, it will start to train the network. And on this computer, training the network probably takes about 8 hours. So it's a bit of time, but in the scheme of things, what you'll be able to do afterwards, it's really nothing. And once you've trained it, it'll create a file. This is our sort of network file, and then we can use it by just going in here and saying predict. This is my trained network here. This is the image that I want to segment. So it's running right now. It should be running on the GPU because I've got everything set up properly. So this will take a few seconds. The result here, maybe you might feel like, oh, it hasn't done a very good job. It actually exports a couple of different images. So maybe I'll just use the channels tool. So maybe you feel like, oh, it hasn't done a very good job for those cells, but that's not actually the case. So if we just look at a channel view, yeah, so channel 2 is actually the segment mask. So this is the result from using the network. And I think that the whole process then took maybe 5 to 10 seconds. So it was actually quite quick. And this is the mask channel that I would use if I was going to make more measurements or something like that. And then just to prove that this, is something, it's already seen this image. So maybe you don't believe me that it's actually any good. So we can use test data or data that it hasn't seen. And then same process, we just come in here and again, this is something that's macro recordable. So Now we've done the hard work of training this network, we can just call this up in a macro and then make it part of our pipeline. So let me just make sure I select the right one. Yeah, and you can see how quick that was. And again, I can just split this up so that we can see the... There's our mask. So, I kind of feel like using Ilastik is great, especially because you can get started quickly and you don't need to do, much effort at the beginning. But if it's a challenging project or speed becomes important, then using a tool like this is much faster and will give you a better result. Actually, one last thing I want to show you, because this is really important and it really highlights why you have to be careful with these tools. If I've gone to the effort of making this model, and I know it's trained well for detecting neurons, but what if I have some data that's captured on a different microscope or maybe with a different resolution? So same image, I'm just going to scale it to 0.5. So maybe I did some binning when I was imaging to image quickly. The data looks the same to me, like I can still see those cells very easily. Like I feel like this should be an easy problem to solve. And if I put it into Ilastik, I'm sure it would do a pretty good job. But what about if I use my network that I've trained on this exact problem? So I'm using the same network. I'm just selecting this cell, this image that I just made. And hopefully what should happen, I should get a pretty poor result. So but I'm hoping this will be a good illustration for you of why you wouldn't want to do this, because this network's been trained on data from a different scale. It's not detecting any cells, even though to us, those images look very similar to the network, they're completely different. And so this is sort of, I hope, brings home that point of, train these networks for a specific task and make sure that you're using them for that task. Because if you start to go outside, what it's been trained for, the results can be very unpredictable. And so I think this is important if you're using this in your research. Train the network, and then when you publish, share the network, have some data there so that people can see exactly how it works. And I think if you're doing things like that, you don't have anything to worry about in terms of using these really advanced tools. Yeah, so that's really what I wanted to share with you today. And hopefully this has been successful in, showing you how these tools are accessible. Even though many labs have sort of approaches that they're using, which is sort of based on techniques that have been handed down, and can be a little bit hesitant of adopting these techniques. I hope I've sort of shown you that these are both powerful, accessible, and reliable tools. And I hope if you've been joining for these series of workshops that you have learned a lot in terms of how to automate projects and feel comfortable, using tools like Fiji for doing this analysis. And hopefully you can also share that knowledge with other people and help them, save a lot of time, but also do rigorous research. Does anyone have any questions? Or yeah, great. Oh, that's great. Yeah, so I think, next year we'll go into some of this stuff in a little bit more detail. And actually in a couple of weeks, we'll do a workshop using NIS elements for using neural networks on the fly. So you could do imaging and segmentation using neural networks. So hopefully that's going to be useful as well. Yeah. Okay, well, we'll wrap it up there. Thank you.